Hello again, it's Jolly. So let's talk about those conjugated systems some more, but let's talk about the very first type of reaction. So I'm going to go to the handout, but we're not going to be there very long. All right, so this is called electrophilic addition. Well, thank you. There's an electrophile when you do any kind of reaction. All right, sometimes it just gives us a visual. But there are two types that we're going to be talking about with conjugated systems, and one of them is called 1,2, and one of them is 1,4. And they can be in competition with each other. We're going to do hydrohalogenation of the alkenes. I'm going to jump over to the whiteboard so that I have more room, though. All right. All right, 1,2 versus 1,4. Now, I am not naming this. I'm going to put them for reference only. But if I have my diene, just arbitrarily, I'm going to number them 1, 2, 3, 4. And I'm going to do hydrohalogenation. So H, X. Now, in this case, there is no difference between those two alkenes. So I'm going to just choose the first one that I numbered. My pi bond is going to be my nucleophile. It's going to attack the acid. And anytime you break a pi bond, you have to put two things in its place. And we're going to use Markovnikov's rule, and we're going to make an allylic carbocation rather than a primary. And so this is where the hydrogen went. All right. Okay, keep track of our locations here. All right, so there is my first stage, if you will. Anytime you go through a carbocation, look out for rearrangement and resonance. This one can have some resonance action. So this would go over there, and it would put the positive right there. And again, our locations, 1, 2, 3, 4. Now, if you have your nucleophile, it's going to come along and attack that carbocation. This one would be in the 1, 2 position, where if you go through the more stable intermediate, and do 1, 2, 3, 4, you would get a 1, whoops, 1, 2, 3, 4. And the 1 is talking about the hydrogen, and the other number is talking about where the halogen is going. Oh, so there's nothing really nifty about this. It's just keeping track of our locations. But anytime you go through an intermediate, are you going to get both products if it can do this resonance? Well, let's talk about why I said one was more stable than the other. So let me draw them both out again, because I like this one. What do I love about it? Okay. Yes, it's secondary. Not really important. It's allylic. Okay, that's what I know about the carbocation. What do I know about the alkene? The alkene is monosubstituted. Okay, let's jump over here. What do I know about my carbocation? Yes, it's primary, but not really an issue. More important is that it's allylic. And what do I know about the double bond? Ooh, it is di-substituted and happens to be drawn trans. So which one is going to be more stable? This one. Now I'm going to throw a term in there. It's more stable thermodynamically. It has an overall lower energy state. So this one is the first one formed, but this is the more stable one formed. So if we're going on rates, we're going to call it kinetic. And if we're going on stability, we're going to call it thermodynamic. but that is a generic 1-2 versus a 1-4. Now we need to see some more variations. Let's look at one that isn't so symmetrical. All right, in this case, what are my choices here? I have this pi bond and I have that pi bond. Well, which one is going to react faster? Remember, the less stable reacts the fastest. So this one is only mono substituted, where this one is di substituted. So I'm going to start with the least stable or the more reactive. Now I could go on and I could do 1-2 addition. Or if I give it time, it can actually go through resonance. And end up with the 1-4 product. Now, is there, a major and a minor here? That depends on the conditions. That depends. So how are we going to control it? Well, the way we control all kinetically useful things with temperature. Now, keep in mind, even if I have this cold, if I let it sit there forever, if it's going to go into equilibrium, eventually it's going to go back and forth until I get the thermodynamic product. But let's just say, it's cold and it's quick and I isolate my product. So if I want the kinetic product, which we're calling the 1-2 because it was the first product formed, okay, we want it cold. All right, what kind of temperatures am I talking here? Yeah, like -80 degrees C. We're talking pretty cold. All right, if I want the thermodynamic product, thermodynamic, which is the 1-4. Now, I'm not necessarily needing heat, but it can be warm. Okay, it just can't be in negative temperatures. So I'm just going to call it warm. All right, what is warm? Completely dependent on the reaction. So again, in my world, anything that is greater than 25 degrees would be considered warm. But pretty much you get the thermodynamic product unless you try and control it. All right, so that is basically the 1-2 versus 1-4 reaction. All right, one note, 1,3-butadiene prefers 1,4 addition with electrophiles other than HCl. HCl is just a little bit more reactive. All right, kinetic control versus thermodynamic control. Kinetic control is dependent on the rate of the product form. Thermodynamic is dependent on the stability of the overall products. And so here's that temperature issue I was talking about. So a -80 degrees, okay, no peroxides because I don't want anti-Markovnikov, okay? I don't want to go through radicals. So make sure we're not in radicals. We're just doing hydrohalogenation under cold temperatures. If it's really cold, 80% 1-2 addition and only 20% 1-4 addition. If you'll notice, even at those temperatures, you're still getting some thermodynamic. Okay, nature loves neutral and it loves the lowest energy state. And ultimately, equilibrium will always favor, okay, the most thermodynamic. But can you get that 1-2 addition? Yes, especially if you can isolate it fast enough. So it should be pretty much the other way around if you add heat. And it is. 20% is 1-2 addition, and then 80% roughly is the 1-4 addition. All right, I'm going to draw you a little picture. I'm going to jump back to that kinetic thermo issue. And I know that is making sense, the kinetic versus the thermo, but I'm going to draw you an energy diagram. All right, so here's your reactants. I know you just love the sound effects. All right, so here's my reactants. Here's my activated complex. And here's my products. Now, if you'll notice, my products are lower, and therefore it's either exogonic, exothermic, depending on which one we're talking about. So it's exo. Woo, I love that. But look at this. That is a huge activation energy. That's a huge activation energy. Okay, well, let's say this is like a 1,2 versus a 1,4. So let's do a green. Here's my reactants. Interesting. It is still lower, but it is not as low or as favorable as the original products. But what's the difference? It has a smaller activation energy. So even though the product ended up higher, it still has a lower activation energy. So this one will still form first because it's faster. Okay, it takes less activation energy. But given time, this one is the most stable. And so it is, if you will, second, but with time. So this one's the thermo. So we have our kinetic versus our thermo. Yeah, Jolly, that of course makes sense. All right, now the interesting thing is, why did I draw this? Because sometimes in molecules, you don't have an energy diagram, and you're going to have to look at it and say, wow, well, which one do I think will be the kinetic product and which one will I believe to be the thermodynamic product? Now, the 1,2 versus 1,4 addition was easy because it went through an intermediate. And that intermediate was very obvious in that there was a difference in its overall stability. But what if you weren't? Okay, what if you weren't given something so nice with that perfect intermediate? Then you would have to inspect it. Okay. Hey, sterics and electronics. And you just roughly do that every time you look at a molecule now. It's kind of ingrained. So if I said, oh, look, there's butane, which hydrogen is going to react the fastest? Well, what reaction are you talking about? Okay, just generically, I would say, based on numbers, so there's 6 primary hydrogens, okay? And those are not sterically hindered. If I didn't have access to that energy diagram, I would call those my kinetic product. Where my secondary, let me see, has 4 hydrogens, and I would call those my thermo product. And again, it could be wrong, but if you're just inspecting it, you need to look for some similarities, some characteristics that we've used in the past. It's really nice though if it goes through an intermediate, because then you can really tell which one is going to be overall more stable. All right, jump back to our notes. All right, so we've got 1,2 versus 1,4 addition. We've got kinetic control versus thermodynamic control. And really, the only one we're going to do is hydrohalogenation. And so on here, this question, basically, I was just putting, can you tell whether that is a 1,2 addition or is that a 1,4 addition and the mechanism? Because for this one, the mechanism will show you the intermediate and it will show you the steps. So see if you can draw the mechanism for each of those. Oh, and then look. Hey, can you determine the products for each of these? I'm so original. Look, I just said cold, like -80 degrees, and it's the same molecule. Again, this is just practice with you doing the same molecule to see how you would get back and forth between both of those intermediates and get 1,2 versus 1,4 addition. All right. That I know seemed too simple, but in a nutshell, conjugated systems, hydrohalogenation, they can go 1,2 versus 1,4, and you will control that using temperature. Until next time, jolly out.